Okay, we're going to be going through section 8, this lecture portion, trigonometric limits. We're going to introduce the squeeze theorem, certainly with an example and an explanation of that. We'll present the squeeze theorem to you. We'll do a squeeze from the squeeze theorem. We'll give you graphs of it, yada, yada, yada. We'll do an important case. This is an important case over here. We'll do cases related to the important case, and we'll talk about that as we go through this, all right? So then we'll do examples, but let's first up is lecture material, all right? Basically, I'm talking through stuff that's presented to you in the notes. So let me do that. I'm gonna go to the whiteboard. Okay, so squeeze theorem, and this is trigonometric limits, by the way. It says on occasion we will be asked to evaluate a limit where our thinking will fail us. And here's a case where most people are going to fail miserably in thinking through the problem. All right. So my claim over here is whether it fails or not, we have techniques to do this. And we'll talk about those techniques in a moment. But the bottom line, if you were asked to do this limit over here, I'm going to point out the methods we'd like you to do is we certainly would like you to do a table. All right. That's something we've done in the beginning. So you might do what's called numerical. What's numerical? Well, you need to come up with a table. What's nice about this problem over here is x is going to 0 from the right. So I'm going to say like, maybe 0.1. And we've done this many times before, 0.01, and then maybe 0.01. So I hope you know that this is going to 0 from the right. The problem is it's going to require a computer to do this part over here. So this part over here is the f of x part. And what's the f of x going to be? Root x. And then you get, 1 plus, and no, I really need a computer to do that, sine squared, 2 pi over x. And I think that's what they want. Yeah. And then what you got to do, you got to compute, you got to compute, you got to compute. And then looking at these three numbers, you would need to do a prediction over here. And I'm going to say, if you did compute those numbers, I'm hoping you'll be able to predict that this does appear to be going to 0 from the top of it. All right. So that's one way to do it. The other way to do it is as a visual. So visual. So what am I doing? I'm graphing out f of x. What's f of x? Well, it's the function I'm interested in, which is root x. 1 plus sine squared, 2 pi over x. The problem with a visual does, so I couldn't do this by hand, but there's a problem with this visual over here. I'm kind of looking at it, and no matter how close I get to this over here, my big concern is I'm wondering what's happening over here. So you keep zooming in, zooming in, zooming in. But I think at some point you start to realize, you know what, maybe it's, whoops, sorry about that. Maybe it's going towards a 0, but I want to point out there's a hole there. But anyway, visual tables are all leading to the same conclusion, that this thing's going towards 0. I don't mind you doing that, all right? But we need to move on, all right? We need to move on. We're going to move on to a theorem, all right? Let's talk about the theorem. And again, one step at a time. What are we doing? We're doing the squeeze theorem. And we'll talk about this example in a moment. The squeeze theorem states if I can find sort of like a sandwich where h is above g and f is below g for all x near a except possibly at a. So we're going to say this inequality holds where g of x is in the middle when x is near a. Now, what does that mean? I want to point out what it means to me is if we're at A, we need to find some open interval where it's going to be true. That means near. We're going to be near, open interval. What they go on to say, though, if you know the limit of the bottom function and the limit of the top function, and they both equal L, we can conclude that the limit of the guy in between is L. All right? So let's take a look at an example. And we'll do this example over here. We're going to use the squeeze theorem. My gut feeling, though, for a lot of students, this can get very, very difficult. So what I'm going to do is I'm going to go through it in stages with you. And I want to point out, we're just going to use prior knowledge. I hope you realize that if I were to write the sign of any argument down, right, any finite number down, that it would definitely be between -1 and 1. No matter what that argument is, as long as it's a finite number, the sign of it will be between 1 and -1, always. All right. How do you know that from Math 120? The next thing, what I would do is I would add 1 to all sides. What do you get? Well, 1 to the left side would be 0, 1 to this side. Well, I'm sorry, I didn't do that yet. I'm sorry. I squared all the sides. I'm hoping if you realize that over there, that, the sign function for any finite number, if I'm squaring it, would always be greater than 0, and it would always be less than 1. All right, things you learn in Math 120. Then what I do, now I'm adding 1 to all sides, 1, 1 to that side, that side. So why would you do that? I'm seeing that right here. Then what did I do? This might seem crazy to you. Well, since the root of x is always positive for x greater than or equal to 0, I have something that's pretty simple. I multiply all sides by root x. So right now I have a squeeze. This squeeze is true for all x greater than 0. It's true for all x greater than 0. All right. So here's the deal. You got the squeeze. All you have to do is look at the limit of the top and the bottom. So we're looking at these limits over here. And what limit looking at? We go towards 0 from the right. We're doing this one. We're doing this one. They both equal 0. What can conclude? By the squeeze theorem, I conclude that guy in the center is also going to, that limit is also going to be 0. All right. They give you an illustration. I want to point out what the illustration is. We graph out f of x. This is x over here. What's this curve over here? That's going to be 2 root x. What's this curve over here? It's root x. What am I seeing? A clear example of a squeeze. So what are we indicating that you probably should be doing over here? Finding a squeeze is difficult. So if you think you find a squeeze, what we recommend is please graph it out to make sure you got the proper squeeze. You want something above, something below, and something in between. All right. So I'm going to say that's not so bad. You can use a calculator if you like. We're going to talk about an important case now. So as I do this over here, someone says, what's the important case? And I have to read. And certainly we're going to encourage that as well. So someone can say, oh, no, I don't read. I just look. No, you got to read. What are they saying over here? Important case. All right. This is an important case. This is important. All right. So I'm going to read it. If it's important, I'm going to read it. It says, if you can recall, you were asked to do this problem numerically, and we found it equal to 1. We also did it visually. You may recall that. You may not recall that. We're hoping if you study, you can recall things though. So I'm going to say, we did that prior. We did it by numerical tables, a numerical method, and I also graphed it. And it was pretty convincing in both cases that was leading to 1. Now what we got to do is we got to really make sense out of this story over here, right? So by reading it. So what we're going to do is we're going to use a geometric argument, and I'm using a unit circle. So I want to point out, I'm seeing the unit circle, and I'm going to just kind of trace it in for you. Now someone says, oh, that's not a unit circle, it's only a quarter one. I definitely see it. If that's a unit circle, I'm going to claim this is the point 1, 0, if that's a unit circle. What's this point over here? Well, if that's a unit circle, this is going to be 0, 1. That's not difficult. And I'm hoping you're not finding it difficult. Again, the reason we provide these exact, I shouldn't say exact, but really high quality images is so you can look at them. We want you to look at them. All right. So I got my unit circle. I know that part. And it says it's a geometric argument, it's a unit circle. Now I said, we're going to label this in class, but label what? I see a bunch of things over here. And claim I'm seeing a green line, I'm seeing a blue line, I'm seeing a black line, I'm seeing all kinds of lines. All right. Now I'm gonna talk about this thing. I'm gonna talk about this as being an angle theta now. And I'm gonna take this point over here, and I want to relate it back to what you learned in Math 120. Just that point over there. So I want to do this point right over here. Just relate back to what I did in Math 20. Well, the whole defining feature of a unit circle was their definition of the trig functions. And what's that point going to be there? Well, the point there is going to be, let's see, sine. Oh, no, it's not sine, it's cosine, right? It's going to be r cosine theta. Well, r is 1. It's a unit circle. So it's going to be cosine theta, comma, sine theta. All right, we got this point over here. All right. I'm looking at other things, and I guess I could, if I wanted to, not that it's important, but I could tell you what that point is, right? If you wanted to. Oh, by the way, this point over here, I could also tell you that. Let me write this point down. Maybe not be important. Let's take a look at it. What's that going to be? Cosine theta, comma, 0. Right, I'm going to look at this point over here and see if I can do that point. I'm seeing a bunch of points here. And I want to look at that. And I'm going to say the x coordinate looks, 1. What's the y coordinate? Let me write this down. So I'm going to write down the tangent of theta. What's tangent theta? It's going to be the opposite side. Well, it's going to be the y, isn't it? Over the adjacent, which is 1. So what's this guy going to be? Just going to be tan theta. Let me get my eraser out. And I'll erase this thing over here. So I'm kind of exhausted, graphing things out. But what I'd like to do is, I'd like to talk about regions now, areas. And so what I'm going to do is I'm going to do an area, a small area. So I want to do the smallest area I can find. And then I want to find another area above that. It could be equal to it, by the way. I'll call it area 2. And I want to find another area, and I'll call it area 3. So I'm going to look at one area at a time. I'm going to try to look at this picture. And by the way, since I don't know what this is related to, I'm just looking at a picture. And I want to look at this guy right over here. And I'll put this down over here for you. I'll be really careful too. And I'll call this my small area. So what's my small area? It's a triangle, right? So it's 1/2 times the base. What's the base of that red triangle? 1. What's the height of that triangle? Let's take a look at it. Oh, which is sine theta. Now, what I want to do is I want to find an area bigger than that. And I'm going to do this now. That's not a triangle, by the way. That's what? That's an area of a sector. I'm hoping you remember the area of a sector, right? Well, maybe we should go through that with you. So the area of a circle is pi r squared, right? The area of a sector is going to be theta parts out of 2 pi parts. So what's it going to be? 1/2 theta r squared. Let's write that down. 1/2 theta, what's r? It's 1. We'll simplify this later. Now what I want to do is I want to, get the next guy. I want to get a bigger guy. And I'm going to look at this triangle. Let's take a look at that. 1/2 times the base. Well, the base is 1. What's the height of that guy, though? Oh, it's tangent theta. All right, I need to get that simplified, and that looks just outrageously difficult to me. I can multiply all sides by 2. What do you get? Sine theta. Oh boy, less than or equal to theta less than or equal to, I'm multiplying by 2, right? And what's tan? Sine theta over cosine theta. Now, by the way, I want to keep it simple. I want to tell you theta is going to be greater than 0 for this picture. Well, if that's true, oh, by the way, maybe I should even refine it even more, that theta, if these objects can exist in this thing over here, but what I mean by the first quadrant, it would be between 0 and pi over 2. I definitely found an open interval where this is true. What do you do over here? Well, I guess I got to divide. I'm going to divide all sides by sine theta. Let's see if I can do that. So what'd you get? 1 theta over sine theta. I'm dividing by sine theta. By the way, I want to point out sine theta in this interval is always greater than 0. I mean, it's really easy to divide that. What do you have here? 1 over cosine theta. So I'm going to use some things I know from pre-calculus. I'm going to take reciprocals of these things. So I'm going to get 1. That's reciprocal 1, by the way. Direction of inequality changes. I have a squeeze. Let's put it down. This squeeze holds for theta between 0 and pi over 2, except that theta can't be 0. Well, squeeze theorem holds. Let's write this down. Limit theta goes to 0 of the lower function, which is cosine theta, that equals 1. The limit as theta goes to 0 of 1 equals 1. So by the squeeze theorem, I can now conclude that the limit as theta goes to 0, you know what I should put down over here? It's really 0 from the right. What do you get over there? 0 from the right. What are you going to get over there? 0 from the right. Sine theta over theta is also equal to 1. And here comes the problem. Well, you didn't really show the whole thing. Well, you know what? You can do other problem. You can take this thing up here and you can flip this so it's down here and do the same exact argument. All right. So I'm going to say I did one side. The other side is going to be really the same argument. What's the other argument going to be? I'm going to now conclude the limit. If I did the other argument where theta was coming from below, that same picture, by the way, you just flip it around. I would use the same argument. So what do we now know? We know this. I'll write this down a little differently. You need to remember that. All right. Let's take a look, see if we finish that. I think so. I think they go through the steps in the notes. Oh, they want me to do an example. All right, let's take a look at an example. And it's going to be this one over here. I'll pull it on the side. And I'll push this over here. And they want me to get this limit over here. They want me to show that this is equal to 0. By the way, there's only one thing I do know. I know this. Let's write this down. I'm going to go through the work. Some teachers in calculus say this needs to be memorized too. I don't think so. That's entirely up to you if you want to memorize it. I can multiply top and bottom by the conjugate of the top, which is cosine theta plus 1. Cosine theta plus 1. Let's see if we can do that. Limit theta goes to 0. The top is going to be cosine squared theta minus 1. That's a conjugate, by the way. And at bottom, you get theta times cosine theta plus 1. I'm going to keep going through it because I can't do the limit yet. I want to see limit theta goes to 0. The top would be sine squared theta. I still have trouble. Cosine theta plus 1. I'm going to keep rewriting it. Limit theta goes to 0. Oh boy, I went too far there. Sine theta over theta times sine theta over cosine theta plus 1. This is the first case where I'm actually able to do the limit. And why is that? Well, this guy's limit is 1. What's this guy's limit? Well, it's going to be 0 over 1, which is 0. What's 1 times 0? It's 0. As they said it was. I'm sorry about that. It's 0. All right. They asked me to show that. We just did that. And that's going to be good. Okay. Some people say, I'm going to memorize that. I don't mind. Memorize it. Go to town. All right. All the work is down there as well. Okay. So we're at the place where, we gave you a short lecture. Then we're going to go through short examples later. And then a chance for you to study and try things on your own. We're encouraging that. Again, if you have any questions or concern, I would recommend you come by during office hours. Furthermore, I would also recommend looking at your textbook and reading. Thank you.